Alright, let's do a quick little tutorial on how to manage regular diode clampers. So if I draw a battery, we'll call it 10 volts. Put a resistor in my circuit, put a diode in my circuit, and I say, here's my test point that I want to measure. We're going to call it E out. Okay? First thing I need to do for our rules, circle my solid state component and label my internal polarities. Alright? Then I take a look at my circuit and I figure out which direction my current is moving in. And we know that our electrons flow out of the bottom of our battery. They establish the first thing they touch, they turn it negative, making the opposite side positive. And the same pattern occurs. Every time those electrons touch the first side of something, they make it negative, the opposite side is positive, and then they work their way back to the battery. If there was no circuit, I could take my voltmeter and I could measure across my battery, and I could see that if I put my common on the negative side of my battery and my voltage measurement on the positive side, that I would measure whatever my battery was supposed to be. In this case, it's 10 volts. Alright? Now, if I look over here, my signs don't match. I have a positive negative and a negative positive. So that makes this no-go, reverse biased, and when we have a no-go, there's no current present because it's the equivalent of an open switch. Okay? Open switch means no flow. If I don't have any current, Ohm's law says volts equals amps times resistance. I have a 0 over here. Anything times 0 could be 1 mega ohm, could be 1 kilo ohm, doesn't matter. It's going to be 0 volts. 0 amps, 0 volts. So I know that I have 0 here. Okay? Kirchhoff's law says my source voltage has to be represented across my drops. So if I have 0 here at my resistor, I got to have all the rest, all 10 volts, are going to be across my diode. Okay? Let's go ahead and take a look at what would happen if we put the battery in reverse. Okay? If I take and I put the battery upside down, keeping the same circuit, now what I need to try to figure out is what way is my current flowing. We know that it's going to go in the opposite direction. So negative, positive, negative, positive. Okay. Now I know that my signs match this time. That means I have a forward go diode. If I have a go, I have 0.7 volts because I'm forward biased. If I have 10 volts on my battery, I got to have 10 volts somewhere over here. 0.7 goes to my diode. That means 9.3 is going to my resistor. And that's how we would take a look at those two circuits. So now, let's take a look at what happens when we introduce an AC source. Okay. Now I'm going to take and I'm going to put an AC source in here. Same circuit. Here's a resistor. Here's a diode. Back to ground. Okay. And we know that this AC source is changing. So this time I'm going to show my positive iteration in blue and my negative iteration in red. Nothing's changed. It's exactly the same as these previous circuits where I threw a battery in there. except that instead my battery would look like a square wave. First it would be positive 10, then it would be negative 10. And it would repeat like that if I was flipping my battery back and forth. Okay? I don't have a battery anymore, now I have a sine wave. So the battery analogy sort of ends, except that the battery shows me what my limits are. What's my high limit? What's my low limit? So let's go through this circuit this time. And I'm going to go ahead and I'm going to circle my solid state component and label my internal polarities again. I'm going to run my, got to go out of the bottom of my battery. Negative, positive, okay. I don't match, I have a no-go. Alright. That no-go means I have no current, I have an open switch, or a reverse biased diode. It means I have 0 volts here. 0 amps, 0 volts. Again, volts equals amps times ohms. If I have 0 amps, I gotta have 0 over here. Anything times 0 is 0. Okay? So if I have 0 volts here, let's say I have 10 volts again on this. Now, what are my volts? I gotta be careful when I get into AC. So if I have 10 volts RMS, I'm going to end up with 14.14 volts peak, and that's what we want over here, volts peak. How I get that is I take my volts AC, or excuse me, volts RMS, divided by 0.707, and that's going to give me my volts peak. Alright? Now, that means that all 14.14 volts are over here. Okay? So, my E out, and we'll check our drops out here in a second, how our drops work. Okay? Here's my negative half of the cycle. Now my signs match. So that means I have 0.7 here and 13.44 up here. Okay? If I do my drops, here's my meter. On my blue half of the cycle, I start at 14.4 on the battery. If I drop over 0 volts, 14.14 minus 0 on the way to 0, my ground is 0. I could go the other way. I could go 0 plus, or I can go 14 minus. 14 minus 13.44 is 0.7. Excuse me, 13 minus 0, I'm on the blue side. 13 minus 0 is 0. Excuse me, 14 minus 0 is 14.14. 14.14 minus 14.14 is 0. So every time I go over something, I have to add or subtract. If I start at 0 and I add 14.14, I get to 14.14. If I add 0 to 14.14, I'm at 14.14. I have a balance. I have half over here and half over here. Okay? If I look at my DC equivalent, I have 10 volts here. I drop over 0. I'm still at 10. 10 minus 10 is 0. Okay? If I go to this one, and I'm going the other direction, now I'm negative 10. Negative 10 moving towards 0. So negative 10 plus 9.3 gets me to negative 0.7. Negative 0.7 plus 0.7 is 0. I have absolute values on my components, but my test points are labeled with polarities. Okay? So that's kind of the final piece of this. What does my graph look like? All right. So I know my limits now. I've converted to peak on my AC. I have 14.14, and I have negative 0.7. Alright? So if I take and I graph this thing, okay, 14.14, negative 14.14, I'm going to go 90, 80, 270, 360. So there's what I kind of look like. We know on the positive iteration that I have free reign to get up to positive 14.4, but on my negative iteration, I peak out at 0.7 at E out. So my diode is clipping that peak off. My waveform will behave normally. But once it gets down to 0.7, it holds right like this. And then when it gets back to here, then it drops. It never goes this low. That was what it was doing before. That's what we measure at the power supply. This is what that clip will do. And it will then repeat. Okay? So I hope that makes a little bit of sense on how we are using our diode clippers. For worksheet 6, you're just going to go through each one of those scenarios, flip the diode over, do your analysis of your components and the drops and what gets what voltage. If there's no current, the resistor's not going to have any voltage. That means the rest of it's going to go to the diode. Okay? And then the question is, where is the diode? Is it up here? Is it down here? Is it forward bias or reverse bias? Is it pointing up or pointing down? So just keep redoing these circuits and you will see patterns emerge. And that should help you figure out how to do this work.